Hello. So for tonight's assignment, we were supposed to graph c of x and then get all the values that we need to in order to graph it correctly. I went ahead and did all the rough work and then put it clean, and then I'm just gonna show it all and go from there. See if it makes any sense, which I really hope it does. So let's kick it. Um, in order to first get an idea of what we're gonna graph, we need to find the domain. Usually, an equation of e of x will have all the real values available, but because we have a quotient on our exponent, there's obviously some values that we cannot plug in because it's going to give us 0, and that's a big no-no. So we end up getting values like all the real numbers except when x equals 1, because that's the one that's going to give us that nasty 0. Um, from there, we go on and we can um, for now pretend that that's gonna be a vertical asymptote. We're gonna check it later, but as a good now, we just keep it here in case it works or not. Now we move to horizontal asymptotes. Um, these are pretty much the values that we're trying to see if our graph is gonna touch it on the y values. Um, if you go and try to find it through limit evaluation, you can see that it gives you some nasty stuff. Once you set it to infinity in direct substitute, you get this nasty thing which goes into nastier, and who knows what that means. Say for negative infinity. So what I ended up doing is trying to see what the end behavior of the graph looks like. So I did a table like this where you can plot big values on both sides of the infinity side, I guess, and then try to compare what this might look like. For the negative side, you can kind of see that the further you go into the negative, you get closer to the value of e, a positive one. And similarly, the closer you get to the positive side of infinity, you get closer to the value of e from upside, so it keeps getting like slightly smaller. So therefore, we can conclude that there is a horizontal asymptote at y equals e. We'll write that down and use it later for plotting. The next step will be finding the increasing or decreasing behavior. The way we do this is by finding the first derivative and then doing some magic work to see like what the behavior is going to look like. I wrote down in the top the original formula just to keep track of it. Once you start doing the first derivative, derivatives of e, it's usually just rewrite this and kick a chain of the argument inside. The chain in this case is going to give you a quotient rule and gets all nasty like this. Looks nasty, but it's really not, so you just rewrite it down. You get this stuff, write it like this, and then you can see your x's cancel and your negative ones add up. So you end up with a little nicer thing like this. Since these two are multiplying, you can just rewrite it on top. And that's it, that's the first derivative. Our domain, you can see that the bottom, the denominator, cannot be equal 0. So the values that are going to end up as 0, it's going to be, again, an x, cannot be 1. So that's what we will call a critical value later, but for now it's just an interesting point. We're going to test it and see if it's a critical value or not. Right here we're going to put it on a line summary, just to try to see what the behavior looks like. So we're going to put our 1 in the middle and have like a couple values on each side just to see what the line is doing. We evaluate each little value on our first derivative, so we set it to 0. Boom, 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 boom. You can see you get a negative value, so it's negative, it's obviously decreasing. Say for the value of 2, we set it up, we solve it, we also get a negative value and it's also decreasing. Since there's no change in behavior, this is not really an inflection point. It is like just an important point to keep in mind, but it's not really a critical value. We're gonna see later on why. So there's no change in behavior, it's always decreasing. Now, usually when you try to find what the point that you cannot plug in is doing, you try to go for the limit. If a limit exists, it usually means that's just a little hole in the graph. But if the limit does not exist, you can try another stuff to figure it out. In this case, once you direct substitute the 1, you get a 2 over 0, which is nonsense. That just means that there is no limit. It's just doing something funky. It's looking like an asymptote. So we do a little table and plug different values from each side of the 1. As we can see, the closer we get to 1, the more it starts looking like a 0. So it's just decreasing for trying to reach 0. And if we go increasing just slightly on the right side, you can see that it wants to go to infinity, which means like it's really different from the negative 0, not a negative 0, close to 0, and close to infinity. These are the values I plugged in to test that. And then because these two limits are not equal, it's most likely that the critical value is going to work as a vertical asymptote at x1. So we're going to write it down and test it later. Extrema wise, because there is no change in behavior and because these limits are not the same, we can conclude that it's going to, on this side, it's going to go on forever on the y-axis, so there is no maximum point on the graph. And on this side, it's going to just trying to go to 0. It's never going to touch it because it keeps getting smaller and smaller, so there's really no lower point, because as soon as you set one out, there's already one even lower trying to like beat the last one kind of thing. So we can conclude that there's no extrema points. We'll leave that for later and graph it. Now, concavity wise, we have to go to our second derivative. So I wrote the first one up here just to remember it. It's a bunch of nasty stuff. I try to color code it just to it's easier to read. But basically we have to do a quotient rule. Low D high minus high D low all over the square of what's below. In this case, the D high is going to be similar to our first function, which is going to kick a chain. I wrote it down at the bottom right here. So nasty stuff. This chain is another quotient rule, which I didn't want to write, but just trust me for now that it's going to be equal to that. So we bring this back up. There we go. And then on this side, we have a simple power rule, but because it's not a cute x, it's going to pop us a chain of 1. You can just pretty much ignore it, because once you distribute it, it doesn't really do much. Now these two right here, they reduce once you multiply them. It's like multiplying by 2, dividing by 2, same thing, so just reduce it. We rewrite it like this, distribute the negative, and then once you distribute the negative, you can factor out that 40e to the mess. Once we factor it, we end up with this little thing, and we can just drop excuse me, sorry, it's been a long day. We can just drop the parentheses because this is just a sum. Once we do that, we can see that these ones cancel, so we end up with just an x, and we just multiply it together, and we end up with this nice little thing, which is our second derivative, which we will be using later on to find concavities. Whoop. Now, to find the concavities, we need to find the roots, or where the x is going to be equal 0. First, to get rid of this, we're going to multiply both sides by the denominator. This is obviously just a 0, and this side it just goes away. Because these are just multiplying each other, we can factor separately. So we take 4x and solve for x, and whoop, we get a nice little 0. Now on this side, it's not so pretty, because e to any power cannot be 0. It's usually, if you plug in negatives, you get little small values. If you plug in a 0, it's going to be a 1, and anything above 0, it's going to be a huge number. We'll try to put it on logarithmic form, and it's still nonsense, because natural log of 0, it's not that. It's actually just like a big old error. So we have our 0 here. We're trying to like plug it in a line summary. And what I also did is plug in the 1 from the vertical asymptote, just in case there's a change in behavior right here, concavity wise. We plug in those values and test them with the second derivative. I'm hoping the math is right. I got a little problem here because my calculator for some reason was thinking that this was a negative 16 and it threw me off. So I double checked like 3 times on different websites and just to make sure it's right. We want to know the negative or positive values that it's going to give us in these intervals. So I choose negative 1, 0.5, and 2. And we get a negative, positive, positive. So it's going to be negative, positive, positive, and it's going to be concave down, up, up. Yep, that's pretty much it. So there's how it's going to look like. All this value from negative infinity up to 0 are going to be concave down, and then it's going to be a inflection point at 0, excuse me, which is going to turn our concave from down to up, from 0 up to 1. I wrote it like this because I want to make sure that it's people are aware that there's an asymptote, and it's going to still be concave up from 1 to infinity, so on this other side. So our inflection point, we found it by setting the original function with an x of 0, just to see on what y value is going to set to. And as you can see, it's just 1 over e. So our graph is a 1 at 0 equals 1 over e is going to flip from concave down to concave up. Yeah, we'll go on from here. Now the easy stuff was real roots or I forgot the word. Xint. We just call it xint for now. So same stuff that we did before. We set it up to 0 at original function, and it's nonsense. Even if we try something funky, it's still nonsense. So we can conclude that there is no x intersection. There we go. That's the word I was looking for. Similarly, for the y intersections, we plug in a value of x0 in our equation. We get 0 plus 1 over negative 1, it's this, which is e to the negative 1. Once you rewrite it, it's 1 over e. So same as our inflection point, it's going to be 0 comma 1 over e, which is mean that's the same point that is going to flip our concavity is going to be also at the y-axis. So now that we've gone through all the information that we need to graph it, we're going to try to graph it. This is kind of what it would look like. The only thing that it's not so accurate, it's this side, because I noticed on Desmos it's actually a little bit further that way, but this is good enough to understand what is going on. So we test all the stuff that we got, domain of all real numbers except where x equals 1. We see it right here, like there's no actual y value for that. Vertical asymptote, it's the same, x equals 1. We can see that there's not allowed to be there. No. Horizontal asymptote, it's a y equals e. I wrote it here in green so it's a little bit more legible. E, it's roughly around 2.71, so it's roughly somewhere around there. Our increasing and decreasing behavior, it's always decreasing, and we can see this by looking at the graph. The next value going to the right to the line, it's always like smaller, so that means it's a negative slope. And it starts negative, and small, and it starts going increasing and negative, increasing. Now this side of the graph is never gonna touch 0; it's always gonna be decreasing, so it checks up. And for this side, the same. It starts negative and super high, and then it starts going, and it started from being highly negative to small negative, but it's always going to be decreasing. Our extrema, there are none. As we can see, this is always going to go to infinity. The closer you get to 1, the more infinite it's going to be. And same down here, the closer you get to 1, the closer it's going to get to 0, and therefore there's a lower point all the time. Real roots or x intersection, there is none, because like we said before, a graph is never going to touch 0. It's always going to be a smaller value, which is virtually a 0, but it's not actual 0, so it's never going to touch x. As for our y intersection, at 0, 1 over e, it's this little green dot right here. As we can see, this is the concavity flip. Unfortunately, I didn't draw the graph big enough to show it more, but this is concave up right here, and then this is concave down, and this side is concave up again. So that's all the information we needed to graph it. I'm hoping it's right. I spent all day and more than what I like to admit working on this, but it's